Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So I'm going to be picking up where I was last time. So last time I talked about a bunch of different things. So I talked about at least a useful definition for what a problem is. It's a rather broad definition. Then we talked about input size a little bit. Remember, that's how, like, if I give you an instance for a problem, it is the number of bits I use to represent that instance. And we usually, for our purposes, we usually consider the number of elements that are in the input, typically. That's most of the time what we're going to run into. Now, I want to touch upon a few things today about algorithms. In particular, we're going to focus primarily on correctness of algorithms. Now, when I usually talk about an algorithm, the one thing I need to really separate is the notion of a computer program from an algorithm. I usually want to be focusing on the algorithm itself, not necessarily its implementation on a computer. And you're going to find that in this course, we're going to focus a lot more on the former than the latter. So you'll find that we're going to focus a lot more on the ideas to get us to the algorithm, not so much how we would implement the algorithm. Because at this stage in your studies, you probably have seen plenty of ways to implement algorithms. You may have seen how to implement some data structures. You may get some experience with doing that in this course as well. But you're going to find that really the thing that makes or breaks whether something works is whether you got the correct idea or not. And that's where really things are going to flourish in this course. So I'm going to kind of go on a little bit of a trip with you today. I'm going to start off with a rather simple problem. This is one I touched upon last day, is the search problem. So we're going to talk a little bit about analysis of algorithms, and we're going to kind of go deeper into this. So recall that last day I said the search problem is if I give you some set S of elements and some element X, I want to determine if X is in S, where S is the set. For our sake, we'll be assuming that the set is given to us as an array. I'm going to make no assumptions about what the elements look like in this array. They're just elements. And we talked about this actually last day. Talked a little bit about this. So just to elaborate on what I mean by this problem. Suppose I give you an array and I call it L. And suppose I have some elements in here. It doesn't matter so much which elements are in here because it's just any one instance of this problem is just some collection of elements. So I don't know, say I have 2, 9, 12, 19, 20, 22, and 26. And each of these in my array will have a position. Starting at position 0, I go 0, 1, 2, 3, 4, 5, 6. So I have 7 elements here in my array. And suppose I give you an element X, and in my array here I have a bunch of numbers. And suppose I said, okay, say X was let's say it's 12. And I wanted to know its location. So one way I can answer this, so if I give you an array, if I want to know if it's in S, in our case that's what L is, where would be the location of 12 in this array? Can somebody tell me? Yeah, it's in position 2. Exactly. So you would say, so if we wanted to encode this problem as I give you an array, you return to me the position for which that element exists, or -1 if, say, that element isn't in the array, you would return back to me, in this case, 2, right? If you wanted to say, okay, is it in S or not, you'd say true. Problem formulation really does matter here. But if I change this up from 12, say instead I change it to, I don't know, let's make it 32. If I ask if 32 is in this array, you'd probably tell me, no, it's not in the array. So if I wanted to know its location, you may pick some magic number that may represent meaning it's not in the array, such as -1, which no position in this array will ever have. So is the problem formulation clear to everybody? So give me 2 thumbs up if we're good with this so far. Okay, great. So last day, it was elaborated on that a way you could solve the problem I just described here is using linear search, right? So that's where we scan the array from left to right. And if we encounter that element, then we could simply say, hey, look, I found it. So I'm just going to simply return its position. But if I go all the way through the array and I don't encounter it, you know it's not in the array because you had to have evaluated all the elements in the array, correct? So I'm going to describe to you one way I could write down linear search. So I'm certain you've seen linear search at least a couple of times. So I'm just going to go a little bit faster with this. But the point of this discussion is about pseudocode. So you might ask, first, I'm not sure how familiar you are with pseudocode. You may have seen it in 2.10. If not, that's okay as well. I'm going to talk a little bit about this, because it's one of these important elements of when you're describing an algorithm. So often algorithms can be described in pseudocode and English. So for example, I will very often in this class describe even algorithms in English to you. And that's why when we talk about an algorithm, we have to be very careful how we describe it. So when I say that, I need to remind you that an important detail for an algorithm, I'm just going to abbreviate with alg, is that it is unambiguously defined. Now, I told you briefly what that meant last time, but I'll spell it out just to be clear. So I'm unambiguous about it. So let's so depending on who is reading an algorithm, it is important to give enough detail to how the algorithm is performed. That's an R right there. It sort of just got smushed in between the E and the F. So when I say this, you got to think about your audience of who you're talking to or who you're communicating this with. Now, this is where it gets very interesting for us, at least as computer science people, is we have to think about it more about how we're talking about the algorithm and how we communicate it to whomever is the audience. If we're trying to describe the algorithm so that we implement it in a programming language, you have to be far more specific than if you're talking to somebody that's, say, an expert in the area that you're maybe discussing. For example, if you were talking to some guy that knows linear search, you probably don't need to give a whole careful description of the pseudocode to them. They'll know what linear search is. However, a computer is not really that bright, right? You have to give it the instructions to do so. So what you would do is you would take the description of the algorithm and you would write it in the programming language, correct? And that's the way we translate that into machine code for the computer to actually process the algorithm, right? So there's a natural analogous relationship between computer programs and this notion of an algorithm, because all of our operations are going to be unambiguously defined, and computers their operations are unambiguously defined as well, right? They're defined on arithmetic, logic, and so on. So is that clear, everybody? So when I say this, you got to think about it mostly from the standpoint of the audience when I say unambiguous. So in the most purest way, it would be that you describe it in the manner so that there's no way you could misinterpret it. I'll tell you a little fun story about this. So there was always this sign that I would always see on the side of a highway. It says Combat Animal Care on it. And it had a phone number and whatnot. It would be off the side of the highway. And somebody tells me, I look at that sign and I'm like, okay, so it says Combat Animal Care. Now, if you looked at that sign, there may be a couple ways you may interpret it, right? It's ambiguous. At least if you're the most literally minded person ever, which computers are, right? Expecting Kung Fu Panda? Yeah, no. So there's a couple ways you can interpret this. Now, the way the business was interpreting this is that it's called Combat Animal Care, like as in that's the name of the business. But if you're the most literally minded person ever, you might look at that and you'd say, hey, look, it's actually saying combat. Is it combat, like combat animal care, or is it combat animal care? Am I battling against animal care? What is it? Animals learning combat. I like where this is going. This is pretty epic. Hey, listen, I consider it a goal if Kung Fu Panda comes up in one of my lectures. Okay? So, anyways, does everybody get the idea? So, we don't want to have situations like this come up when we're describing our algorithms to somebody. Don't tell Peter, okay? I apologize. Sorry, I'm just joking around here, just to be honest. I'm just having a little bit of fun with everybody. So, anyways, that being said, I want to give you some pseudocode for a linear search. So let's head on over here. So you'll find in this course that sometimes I'll describe it in a programming-like syntax. They'll use very similar kinds of constructions that you would use. The point is that it's exact enough that you can understand and read it. Or I could describe an algorithm to you in words. You'll find very often in this course, that's almost always how I do them. Now let me just fix my video here. For some reason, it decided to go all funny on me. Let's fix that. My apologies. Although it was pretty epic. There we go. There we go. Wonderful. So, you got a message from the cat. Awesome. Okay, so I must stress that there is no standard way of talking about pseudocode, like what conventions you follow. So just to be clear, I will follow a consistent set of standards whenever I write pseudocode up here on the board. I find it's very helpful for students to see some standard way of doing it. And then you can figure out ways that maybe it might mesh a little bit more for your style. Usually you look at what your authors in your community are looking and how they write things. I'll give you a couple pointers about this. So, for example, here's how I'm going to describe linear search for you. So I'm going to call it linear search. I'm going to have an array L. I'm going to give it also the length of the array. I don't have to, but I just would like to have n somewhere because I'm going to use it in my algorithm description. And x is going to be that element that I was referring to. So the input. So remember, I'm going to always try to classify my problems by their input and output. So whenever I describe an algorithm to you, I got to tell you what the inputs are and what the output, what the output of the algorithm will be. So an array L of size n And I'm going to just call it a value. I'll call it value x. And as output is going to be position I such that L sub I is equal to x if x is in L, and minus 1 otherwise, meaning that x is not in L. So anyways, I'm going to give you a couple of things I'm going to point out about the way I'm going to write pseudocode for you. The first one I'm going to point out is that I'm going to take advantage of short-circuiting when the way I write this. If you're not familiar with short-circuiting in programming is where, say for example, you have it where you have two conditions that can happen. Rather than evaluating all the conditions of, say, an if statement, if you know the first one is false, you don't evaluate all the remaining ones. This is a very common thing that happens in a lot of programming languages. So you'll see what I mean when I write this out. So I'm going to use an arrow like this, a left arrow, to mean assignment. Some other people like to also use, and sometimes I've used it before, sometimes people like to use the colon with an equal sign. In mathematics, they usually, well, to try an M word, the mayonnaise, they use that as define as. So it's very natural to use in this setting. In fact, some programming languages even use this. So if you like that, you can use that. If you like this arrow, you're welcome to use that too. While I is less than n, and L sub I is not equal to x, we're going to do the following. We're just going to assign I to be I plus 1. So we're just going to increment it by 1. And then, so I must stress that I'm indenting this in to indicate that this belongs to the while loop. So when it comes after this, I'm going to line up here just to say, hey, look, like keep in mind, if it's ever unclear, I'll usually use curly braces or just braces. Usually it's very helpful when you're writing things out to be, like I said, be as clear as possible. So I'm going to just check if, yes. Sure, I will, sure, I will do that. I will get that. There we go. There we go. Hopefully that fixed it. There we go. Okay, so if I is equal to n, then so if I is equal to n, that means that I went all the way to the furthest right of the array, and I just went one position beyond the end of the array, right? So if I is equal to n, then I'm just going to return -1. Otherwise, I return the position. Now you might ask, Dan, you could have done the check inside this loop here. Why didn't you do that? Now I could have. Most certainly I could have. You'll find that sometimes the way you present an algorithm actually makes it a little easier to prove properties about it, which is kind of weird at first to hear, because you say, okay, well, it shouldn't matter if it's in a while loop where I'm checking an if statement inside here, or I do it later. But you'd usually say, okay, well, it probably would go a little faster if I put it in here, right? Well, this is one of the things they don't tell you a lot in a lot of computer science classes, is that when you present an algorithm to somebody, it's also not just about the functionality or utility of the algorithm. It's about, is the algorithm actually correct, and how can I argue to you that it's actually correct? So I'm going to present it this way, but I must stress that I could have written linear search in a different way to you as well, right? There's several different ways I could have wrote down linear search for you. But would everybody agree with me that this is okay? That this is linear search as you know it, right? It's just that I wrote it in this specific way. This is just to make it a little easier for you to identify control structures or key phrases. So when I underline the while, it's just to make it a little easier to see what parts are the control structures or what parts are key phrases that are being used. So I usually do it for control structures just to make it a little easier for you to spot them. If you actually look at my notes, they're going to be boldface. But you can take a look at that later. But yeah, so I usually do that to make it so they stick out. But you don't have to. It's just something to make it a little easier to spot everything. But yeah, no. So like I said, this is just one way you could write out your pseudocode. So notice that if I wanted to, I could put curly braces in here just like you would in a typical programming language. You could. The only thing I will warn you about is that you'll notice that I use this left arrow to use for assignment. Because remember, in a programming language, when you see that equal sign, that's really assignment. So if you choose to use the equal sign in your pseudocode as assignment, you have to make sure it's very clear that wherever you're doing a comparison, that you're not confusing the reader. Because now if I wrote down this right here, what does this mean if equal sign means assignment now? So just be careful when you're doing this kind of stuff. So if in that circumstance, what you would do, for example, this is one way you could go about it, is you could have it where you use the equal sign as assignment, but you'd have to write it out like in a programming language where you would have it where it's like exclamation mark equals and so on, just like you would in something like C++. But like I said, I usually like to use these types of approaches so that it's less symbols for me to write down. But are there any questions about my pseudocode here before we proceed? But yeah, you're going to see a lot of pseudocode in this course. So don't worry, this won't be the only time you're going to see this. So if we're good with this, let's proceed then. We're going to talk about proof of correctness. Now, I'm not sure what the detail you went into this in 210, so I'm going to talk a little bit about it. And I will also give you an additional example for those that have taken, say, their second year math class with some of those proof techniques in it, because you will see a lot of those proof techniques come up in this course. They will come up a lot in this class. So if you thought induction was going away anytime soon, nah, man, it's not going away. Or contradiction, those are not going away. They're a very important part of this course. These proof techniques are very fundamental for how we check if an algorithm actually is correct or not. Yeah, the mayonnaise. It really is an important aspect of algorithm development. So we're going to talk about proof of correctness. So I'm going to give you some examples today, and I'll give you an additional example that uses induction. I'm not going to be finicky, just for a heads up, because on the first assignment, I'm going to ask you to try to prove the correctness of an algorithm on your first assignment. I'm not going to be very finicky about which of the approaches that I'm going to present you use. It honestly doesn't matter, as long as you know how to do it. So you're going to get an opportunity to try doing this for yourself on the first assignment. But it's okay. If you find yourself just like, okay, well, I have no idea what Dan's going to be talking to me about, that's okay too, because I will be reminding you about how these arguments work. And also I actually have on the course website actually a review that walks you through several examples of how to make these types of arguments. So if you find yourself really just wanting to see more examples, I have lots of examples on the course website. And there's an optional reading and a video I have there you can check out. But don't worry, I will be reminding people about how if I use or require you to use one of these arguments, I will remind you how it works, okay? For those that, especially if they don't have that background. So the first thing I need to talk to you about is the notion of correctness. So remember back last day, I drew that picture for you and I said, okay, if I have a problem and I have all these instances and all those dots, right? And it's possible that the number of instances is some infinite number. It's infinite. Now I have a question for you. This is a question I usually, like when I used to teach I used to teach courses on analysis of algorithms just itself in the past at other schools, for example. The first thing I would normally ask students was, can you write a computer program to check all those instances? And you'd be very surprised to that people would tell you that they think that that's possible, which sounds very strange to hear for someone like me. But at the same time, this is one of those things where you're exposed to some of these ideas it's for the first time. So it's very interesting when you hear somebody like me come along and tell you, yeah, no, that mayonnaise, the M word, that stuff's actually really important for checking if an algorithm actually is correct or not. Because if I have a problem and it has an infinite number of instances, and I'm just taking those arbitrary problem possible, there may be very specific circumstances where this statement may not apply. But if I have an infinite number of instances, could I possibly just, like if I took one of those algorithms, like my linear search over there, could I conceivably take every possible instance that could possibly exist, run it on a computer with my linear search over there, if I implemented it, say in C++, and put it on a computer? Could I check every possible instance in finite time? Correct, yeah. So like I can't check them all. I need more time. Yes, if I'm restricted to finite time, I don't have enough time to do that. I think I'll be long gone after that computer program. Actually, I don't even think that computer program's even going to halt, right? It's just going to keep checking more instances. There's always going to be another one. When somebody tells you, okay, so what exactly do you do if you have an algorithm and you don't, and say they check 10,000 instances. Now, in practice, if you're doing testing, that's one thing. But that's different from the claim that I tell you that if I told you that that algorithm is correct and no matter which instance you feed to it, it works. That's a different claim, right? These are two different claims. So in practice, you may test empirically, for example, if an algorithm is effective or not, but you won't be able to check all the instances for any one arbitrary problem. So just keep that in mind when we think about problem solving with respect to an algorithm. So that's one of those things we have to keep in mind when we're doing this kind of stuff. So the claims that we're making in this course very often aren't just going to be, oh yeah, it worked when I tried like 10,000 uniform instances that I just generated randomly. That is not the threshold that we're working at in this course. We'll be working at a higher threshold. So we will want to know if the algorithm's correct or incorrect. Is that clear, everybody? So a common theme that you're going to find in this course is that we're going to rely a lot on mathematical reasoning, there's that M word, mathematical reasoning to ensure that if a claim is made, that is in fact true, mathematically speaking. And the most standard way of doing this is through mathematical proof. So you're going to find that when I give you a claim and I say something to you, the burden I have to present to you now is a proof. Just to be clear with everybody. So you're not allowed to let me get away with anything. So my kind of the mode of reasoning I'm going to be working at is I have to either present you a proof or I'll tell you it's true, but I won't have time to show it to you. Okay? So is that clear, everybody? So I'm going to say these proofs can take many forms. So you might ask, Dan, is there some like standard way you can always come up with a proof of correctness? The answer is no, typically. You always take into consideration what the algorithm is, and then you have to figure out a way to argue its correctness, depending on what the algorithm does. It's just like any other mathematical claim somebody gives you. So if somebody gives you some claim about the parity of two even numbers, if I add them together, or something like that, we're in the same game, okay? So just be aware of that fact. So they can take many forms. And arguments employed depend on the algorithm. So just some examples of techniques that we may use in this course are direct proofs. So this is where, for example, somebody tells you, okay, I'm going to exhaust out all the possibilities of what the algorithm is capable of doing. That's an example of a direct proof. So they may do a proof via cases. I'm going to give you an example actually of one of these shortly. So for example, for your first assignment, that'll be probably the most, the algorithm should be simple enough that you should be able to use this approach. Another way is indirect. So one of the more common techniques that you'll run into, and we will talk about what this is about as well when we get there, is contradiction. Another technique is called an invariant. So I will have an example in the notes of what one of these invariants would look like. But for the assignment, it's not, you can choose to do it, but I'm not going to require you to do it at all. So, and then closely related to an invariant is mathematical induction. In fact, you've seen invariants probably before. You just maybe weren't given a name for it. Maybe. You may have been told it, may not have been. I'm not sure. Check and let me know. For example, when you've seen, say in 210, if you've seen a certain data structure, and somebody tells you, okay, whenever I do an insertion into my data structure, at some point before I perform this operation, it satisfies some property. After I do the operation, I want to ensure that that property still is maintained. So a classic example of this that you may or may not have seen in 210 is an AVL tree, for example. When you see an AVL tree, this is one of those self-balancing trees. For example, in that course, well, in 210, you may have seen this, where what happens is every time you perform an operation on the AVL tree, like an insertion or a removal, those are the ones that mutate the tree. What you would like it to happen is that every time before you do the operation, it maintains a property about its height. And then after you do the operation, in this case, an insertion or a removal, that it still maintains the property of the tree. In this case, and well, in that specific case, it's the height balance property. But hopefully everybody gets the idea, is that the whole idea is that the way you would prove the correctness is that you would check every single, so you check the preconditions versus the post conditions. What happened before, what had to be the case before, and what happened afterwards. And just see if it still satisfies the property. And the mechanism underlying this is mathematical induction. Okay? So are there any questions about this before I proceed? It sounds like a lot I'm throwing at you, but it's actually not. A lot of these bits and pieces, you've actually seen them. It's just that they may or may not have been spelled out to you like this. Okay. So if there aren't any questions, let me proceed. So let me give you a definition for if an algorithm is correct. An algorithm is correct if for every instance, so I'm just saying something I said the other day, is if for every instance of the problem, the algorithm always produces correct output. It seems rather straightforward, right? That, yeah, no, every one of those dots, just like I showed you that picture last day that at the end of lecture. This is just me saying that in words. So You might ask, Dan, what's a typical way of approaching this? And here's a pretty standard way of doing it. So we prove there's two conditions that we're going to be really interested in this course. Because our algorithms are going to have to terminate in finite time. So that's the first condition, is termination. So termination, that's the first condition. The algorithm terminates in finite time. And the other one you might naturally guess from this definition I have here is that it has to always produce correct output. The one neat thing about this, so let me just write that second part first before I proceed, because I know I will start talking a little bit more here, and I'd rather make sure we have this written down. So correct output. This is just simply that the algorithm produces correct output. You might ask, Dan, this seems rather straightforward. Like, I get this idea. Why are you spelling this out? It's very important because we have to make sure we have clear definitions for everything that we're doing, okay? So you might ask, Dan, if you can guarantee me that the output's always correct, you don't necessarily have to prove this condition. Because if you can guarantee me that the algorithm always terminates implicitly by giving me correct output, you might say, okay, then I don't. So you'll find very often when somebody gives you a proof of correctness that it's sort of baked into this second condition a lot of the time. When we're going to see some of the algorithms later on in this course, you'll see that I won't really implicitly prove this property. Explicitly, I should be a bit more precise. I wouldn't explicitly prove this property. It'll oftentimes be a part of this second condition. However, the reason why I put these both separate like this is because very often, if you can show first that the algorithm always terminates, then you can make inferences about the correctness of the output. And we're going to see that in our example here. So that's why usually it's a good idea to kind of separate these two out. Sometimes it is actually quite helpful when you're trying to prove a property about your algorithm. So is that okay with everybody? So I'm going to show you an example of how we're going to go about doing this. Like I said, this isn't the only way of proving the correctness of our algorithm over there. We have linear search here. So let's head over here. I just want to point out a few things about linear search that are going to come up in our proof. And I want to walk you through kind of that mentality, the mentality to help think about how we can establish that this algorithm always works. Now, this algorithm is very simple. So the techniques that we're going to throw at this are going to be naturally quite simple, at least from a formal standpoint. And that's usually a nice hallmark of a nice algorithm, is that one thing is that if I give you a nice simple algorithm, I can easily check its correctness, right? That's a lovely property for an algorithm to have. That's why linear search is often kind of the whipping boy of these algorithm kind of exercises. So there's a few things I want to point out to you. So about those two conditions I gave you over there, about termination and correct output. The reason why I presented it to you, because I like to show you all my cards, the reason why I presented it like this to you, where are the exit points of this algorithm? Like where does it terminate? Does it terminate inside this while loop? Where does it terminate? On the returns down here, after the loop. Does everybody see that? So notice, so one thing that you can notice very quickly is if I can guarantee you that this loop finishes, and I just tell you, oh yeah, it's going to return here. If I know for absolute certain fact here, I'm being a little redundant with you, if I have it so I can guarantee you terminates, you know there's exactly two cases that can happen. Does everybody see that? There's only this if and the else, right? There's exactly two cases here. Does everybody see that? So this is where one of those really handy things that I really wanted to point out to you. So the way somebody presents an algorithm to you may not necessarily be the most efficient way of doing it, but You could easily see a way you could rewrite it so it's a little faster if you wanted to in practice. But this is just meant to be more of an example, just to illustrate the way you could present an algorithm. It can be very helpful for establishing the correctness here. In our case, this is the game plan. So I usually like to tell students about a game plan. What's kind of the strategy we're going to use to prove the correctness of what we're trying to establish. So my game plan is I'm going to prove that it terminates in finite time. Now, for this case, it's going to be really nice and easy for us. Why? Because notice this condition right here. There's this one right here, right? And you know that this while loop's always going to increase I by 1. So you know for sure, regardless of whatever that condition's doing over there, you know this while loop has to finish, right? Because n is a finite number. So you're going to see that that's going to come up in the first part of the proof. And then once I know that it terminates in finite time, then I can argue to you that there's exactly two cases. Either this happens or that happens. And then all I have to do is tell you what the algorithm does in those two cases. And then from there, we argue that, yeah, it actually does, it gives us the correct answer. And how we do it is established based on these two conditions on our while loop. It's kind of neat like that. So does everybody understand the game plan? So I'm going to formalize this a little bit down. I'll write it in words. It's going to seem a little strange depending on how you came into this course, how this was, but that's okay. Don't worry. Believe me, it all starts somewhere. So let's proceed. Because a big part of this course is trying and figuring out these things for yourself. It's really getting yourself some time to really try to flex your reasoning skills. That's one thing that you need to take out of this, is that I'm trying to encourage you to think about the correctness of the algorithms as opposed to just saying, here's an algorithm, it's a magical thing that popped out of the ether. It's not. It's something that you can actually rationally argue about. So I want to make sure that it's clear, and that's what we're going to find very much in this course, where the ideas are not going to just come out of the magic ether. At some point, it maybe was a matter of intuition, but I'm going to try to give you some reasoning behind where the algorithm comes from. So let's prove the correctness of linear search. So let's start off with the first claim. Linear search terminates in finite time. So this is the first claim I could think of to try to do. Now, we're going to use the same argument that I just kind of outlined to you. So here's how I would go about it. Now, keep in mind, this isn't the only argument you can use, but this is most certainly a very natural one if you wanted to go about this directly. I must stress that if you found yourself staring at this and like, okay, well, it's a loop, I could potentially use induction, for example, on the length of the array, for example. That's another way you can actually go about this. But because this algorithm is nice and simple, I can use a direct method like this. So to prove the claim, oh no, my little turtle, the Java turtle fell. Weep for the turtle. So to prove the claim, observe at the beginning of the algorithm variable I is set to 0, and after each iteration of the while loop, the value of I is increased by 1. Now, here's where things are going to get fun. Yeah, exactly. If the Java turtle was a ninja turtle. Actually, I guess it's a ninja turtle now, I guess. But anyways. So, just to make this a little easier for you to see, I'm just going to suppose that this thing doesn't actually terminate. But keep in mind, at this stage, all you would have to say, well, one way of arguing this, the one thing I could say is that if all you have to do is invoke the property I said before, is that notice that one of the conditions of the while loop is that I is less than n, but n is a finite number. So you know that that while loop has to cease, right? Has to end. But I'll write it this way just because I think it's a little bit more fun. If the while loop performed an infinite number of iterations, then the value I would be unbounded. Right? That would mean that you could just keep increasing I by 1 all the time. It's over and over again. But that's not how this algorithm works, right? Semicolon. However, the while loop requires that I is less than n. The while loop will end as soon as I is equal to n. Therefore, the algorithm. So make sure you always, when you're writing out a proof like this, make sure you always include in conclusion. So make sure you include, just say therefore. I recommend using the word therefore. Don't use the 3 dots. This isn't a symbolic proof. So I say therefore. Therefore, the algorithm terminates in finite time. And to indicate the end of the proof, I use a box. So this box is used to indicate the end of a mathematical proof. So is this proof clear to everybody? Is there anything you could poke holes in about this proof? Is it clear to everybody? So this is how I could present to you what I just described in words. So you'll notice that this proof is effectively what I told you earlier, just verbally. See, that's what you could tell somebody when somebody asks you, okay, well, why do you think it terminates in finite time? And just pointing out those properties about the algorithm is really what you're looking for. You expose properties about the algorithm. That's your goal. So notice that I make an observation, and then I use this to make an argument. So I formulate an argument around the observation. So this is the property I'm taking advantage of, is the fact that this variable I plays a very close role in how it terminates. So all I do is I say, okay, it starts off as 0, and then after each iteration of this while loop, it just increases by 1. That's what the loop does, right? This is not to be confused with me literally describing the algorithm to you. That's not what I'm doing here. What I'm doing here is actually making an argument about it terminating in finite time. This is the observation. This is me describing what the algorithm does up here. However, it's actually an argument about it terminating in finite time. So I just want to make sure I mention that because it's a common pitfall when writing out proofs of correctness, is that students usually just think it's just like you're literally just writing out what the algorithm does, which the observation is usually what is that factor s, but that's not really what's happening. I'm trying to argue to you that the algorithm terminates in finite time, right? So this is the observation, and then I make an argument about it. I say, hey, look, this is the observation, and look, all that happens is if it were not to terminate, that would make absolutely no sense. Okay? So that's the first part here. The second part is the correct output part. So let's head on over here. And I alluded to this earlier. I told you that, oh yeah, no. What's going to happen is that because the algorithm terminates in finite time, you can guarantee that it's going to fall into two cases. So all I have to do is do a proof via cases. Now, for those who have never heard of that phrase before, all it means is, remember, my claim is that this algorithm always produces correct output. So all I'm going to do now is take that remember my picture with my weird oblique, my weird oval-like shape with all my dots in it. All I'm going to do is break that into two cases. The instances that are going to cause it to return -1 and those that are not going to return -1. So that's how the reasoning is going to play out for us. So that's how the proof via cases works, is because there's going to be two boxes that all of the instances are going to fall into because the algorithm terminates in finite time. Does everybody see that? So there's going to be those that are going to return -1 if I give that instance to the algorithm, and there's going to be those that are just going to return something else. The point is that now I have these two boxes. My job is to argue to you that those two boxes, in fact, are going to operate the way I tell you they will. Okay? So linear search outputs the correct answer. So this is my second claim. And once I have this, then I can tell you that linear search is correct. So I'm just going to assume that we have that claim over there, that it terminates in finite time. If it's ever unclear to a reader, you can always just say, well, we previously established that the algorithm terminates in finite time. Hence, we bring us right here. So this is that right here part. So I'm going to just implicitly break it into the two cases just for the purposes of time. The final line of the algorithm returns the value I. Now, if that happens, why did it have to happen? So now this is where it gets kind of neat. Is that, remember back to what I said earlier about there's those two conditions of the while loop. You use these observations to make your argument. So remember, if it returns I, that means it had to have left that while loop before it turned and set I to be n, right? But if that were to happen, that means that that condition saying, oh yeah, there's that you're checking if they're not equal, right? But if it's equal, it's going to falsify that second condition, and you're going to leave the while loop, right? And that's exactly what we're going to say. So this is actually the easy case. This is the correct value to return. As the while loop ended, and I is less than n. Now, but what does that mean? Well, there was that condition on the while loop, right? Which implies, so this is me making a logical inference, which implies that we falsified that condition, which was L sub I is not equal to X. But if we falsify that, that means that that condition is not true anymore, which means what? It means L, which implies that L sub I is equal to X, right? Boom, right? So that's the first case. This is the one that tells us the correct position, if it exists. And the other one is just simply where we find out, oh yeah, it's not in there. Now we must show that the algorithm returns -1. Now, if you've never heard of if and only if, I'm going to explain it in very plain English for you. So, returns -1 if and only if. Only if. This is a very strong statement to make, mathematically speaking. If and only if the value x is not in L. So if you're wondering what if and only if means, logically speaking, all it is me saying is the following. The stuff that comes before the if and only if that's true, it must be that what follows the if and only if has to also be true. If the value x is not in L, if this is false, then it has to be that this algorithm doesn't return -1. So true, true, false, false. It has to be one or the other. There's no way where one of them is going to be true and then the other one's going to be false or vice versa. Yes, please, please. If you're doing this when you're writing this up, you're gonna notice I'm gonna start using either IFF as an abbreviation, or I'll use double thick arrows like this. So if and only if, or I use these the double-sided arrow like this. So you'll find very often I'll use those as abbreviations for if and only if. But thanks for asking that. That's actually a perfect segue for me to do that. See, this is why I like having people bring up things, because it makes a part of the lecture. Wonderful. So you're going to find I'm going to say a lot of stuff that I said earlier, because to show that it doesn't exist in the array means I'm going to have to effectively argue something about how we're going to have to go through all the elements in the array, right? So it's going to be kind of similar to what I said over here on this board over here. So when the algorithm begins, it sets I to value 0, and then I is increased by 1 in each iteration of the while loop. Now, every time we increase I by 1, the reason why we did that is because both of the conditions of the while loop were still being held, right? That's going to be where we're going to make our observation. So for I to be increased, in an iteration of the loop, it must be that both I is less than n and L sub I is not equal to x. Both of these have to be true for me to keep increasing I, right? So, let me finish the argument over on this board. So let's head over here. You might ask, Dan, are we going to do this every single time? No. I just want to illustrate this idea for you. So that way you've seen a full, proper example. Sometimes we'll do it. Sometimes we won't, because I want to save you some sanity, okay? For the sake of time. But I will oftentimes try to give you plenty of examples so you can see a lot of different ways we can argue the correctness of algorithms. But I want to make sure you see one of these properly. Okay, so now we have those two conditions. We know that they have to stay true for I to get increased by 1, right? So, what does that mean? This means that the algorithm compares the value of x against each value in L, right? But remember, if we're going to start off by arguing that the algorithm's going to have to return -1, right? Well, to have that happen, we know that that's when we have I is equal to n, right? But what does that mean? That means that I had to do this, right? So if at the end of the while loop, the condition I is less than n is false, then I has to be equal to n, right? Because we only increase I by 1 each time. The minute that becomes false over there, then this has to happen, right? And the algorithm has checked all values in L, right? All the values in L and none equal x. Hence the return. So this is my conclusion, hence the return value -1 is correct. Now, if I wanted to be fancy-pantsy, what I would do is I would say, well, because the algorithm it terminates in finite time, it must either return I or it returns -1. We've considered all possible instances, and hence linear search outputs correct output. I'm not going to worry too much about that in this course, as long as you have a basic conclusion that is clear for the reader, okay? Because we anyway broke up the proof into a couple pieces anyways. And that's the end of the proof. Are there any questions about this? So remember, it's all about finding some interesting property about the algorithm, make an argument about that property about the algorithm, and then just walk us through how that plays out with the algorithm, and then just say, hey, look. Because of that observation, it has to be that this thing occurs with the algorithm, and that gets you to your conclusion. There's a finesse to doing this, and it's not something that comes immediately to mind. So you'll find very often when you look at an algorithm, you might sit there for a while and be like, okay, well, how do I argue this? That's pretty common. So if this looks a little alien at first, that's fine. So question, how do you feel about using code notation for pseudocode? I'm inclined to use not equal and equals. That's fine, as long as it's clear. So if you're doing this on a test, for example, just make sure you mention maybe at the top, say double equals means equals, not equals means not equal, like with the exclamation mark and equals. If ever it becomes unclear for a reader, okay? That's the only thing. Most of the time when we write out our algorithms, you'll find that you may not have it where it's not equals and equals will pop up. But if it does, that's why you'll find that I use different symbols. It just makes it less ambiguous, but there's no problem with doing that. That's a wonderful question. Okay, so I have a question for you, just as a follow-up for this one. How do I show if an algorithm isn't actually correct? Can somebody tell me? If I told you, here's this algorithm, can somebody tell me, how do I tell you that your algorithm doesn't work? Yes, exactly. I'm seeing it perfectly in the chat. Wonderful. So all you have to do is identify one instance of your problem, and then you just show that that instance fails to produce correct output, or even, for example, doesn't even terminate with your algorithm. Typically, correct output is the easiest way of going about it. All you need to do is just find one instance. That's all your job is to do. Just a single instance. Identify what we would call a counterexample. All you need is a single instance. Present that to the person and say, hey, look, here's an instance where your algorithm doesn't work. And just explain to them why it doesn't work. That's it. So I'll just make a note about that. To disprove, the correctness of an algorithm, present an instance where, that says where. It looks kind of like it's melting into when. It says where. My apologies. Where the algorithm fails to do what is claimed. And the fancy name for this is a counterexample. Like I said, a lot of those reasoning skills come into play, and it's very helpful. Exactly. So I'm going to put into the notes an example for another example of proving the correctness of linear search, except it's going to be done using one of these, what I call an invariant. So it uses mathematical induction to prove the claim. I'm going to put an example of this. I'm going to encourage you to read it. I'm not going to require you to use this technique in this course at all. So just to be very clear, if you go look at it and you're like, okay, I'm not as cozy with induction, just try to understand it, but I'm not going to require you to do it, okay? But I just want to make sure I've exposed you to that technique. Okay? So are there any questions about proof of correctness? Okay. So there's a lovely question in the chat. I'm going to take a look at that. Let's take a look at that. I just had to grab my mouse. Okay. So what if the algorithm works to say all numbers up to digits, and as soon as the input becomes 6 digits, it won't work? Essentially, my question is, how would we identify this instance, assuming we don't have the information that the algorithm only works up to 5 digits? Okay. So now this is where it gets actually quite interesting, because it's very similar to the claim that we talked about with proof of correctness. But this is the neat part. And I will use the example from the dreaded M word, the mayonnaise. Mayonnaise on those sandwiches. Though mayonnaise on sandwiches is pretty good sometimes. Sometimes when you want to identify a counterexample, a lot of people in computer science will actually use a program to try to identify this. So for certain claims, for example, you may try to pull out a computer and actually try to just keep running many examples until you try to run into it, if it's very unclear that it's there. However, like what you had mentioned about the 5 digits versus the 6 digits, if you can't go that high, so for example, if there may be an instance where the array, for example, for our problem here, if I give you an array that has, say, a 1 followed by 10, let's say 1.5 million digits afterwards, to check that instance might take a while. In fact, it's quite big, right? Like that's a lot of digits. To actually check that manually would be very difficult. But this is where intuition is very helpful. So when you try to break an algorithm by presenting a counterexample, the biggest part is figuring out the intuition behind the algorithm, how it works. Figure out and understand what the algorithm is, and then see if you can find or poke a hole in how the algorithm operates. I like to think of it like outsmarting the algorithm. So you find something that the algorithm just does not account for, and you expose that property. And the cool part about this is if somebody actually gave you a proof of correctness, that reasoning may be able to be exposed in their proof. Okay? So in practice, some people, if you want to find a counterexample, it's kind of like testing. You might be able to try checking for a whole bunch of instances and see if you can run into it. Or, so you might like brute force it. For example, when some people make number theoretic claims about prime numbers or certain kinds of prime numbers, some people run computer programs. There's computer programs out there at some universities that have been running for like decades, checking prime numbers or like twin primes and things like that. And sometimes people check these weird conjectures sometimes, and people still check these things and using computer programs. And I'm not even kidding. There's some programs out there that have been running longer than probably some people in this room. I'm just saying, it's kind of wild. But my point is that you don't have to do that. If you have the intuition behind the algorithm, that's also a very helpful tool. And so you don't need to go out and implement the algorithm. You could just try to identify a property about that and expose a flaw in it. And that's very commonly how it's done. Okay? I want to go end off with one small detail, and then we'll pick it up next time, okay? So let's talk about one last thing. I think this is actually an excellent thing for us this last talk about before we get to kind of our next thing I want to chat about. I want to talk a little bit about algorithms just generally. So, let's talk about complexity analysis just briefly. We're going to talk about it for a minute or two here before we leave for today. So, I want to ask you, what are some desirable characteristics for algorithms? So we can compare them. Does anybody have any ideas? What kind of things can you think about or as like characteristics that we can look at about algorithms so that we can compare one and say, okay, this one's better than that one in this regard, and so on? So I see some interesting suggestions. First one I spotted there was space or memory usage. That's a very good one. I also seen one about implementation. That's also actually a very nice thing to also consider. Difficulty of implementation. For example, if you had one programming language, is it really easy to just write it out in a programming language? Sometimes you actually do run into the weird esoteric case where an algorithm is really complicated looking on paper, and it may actually be very simple to implement on a computer. But the neat thing is sometimes that happens in reverse, where you have something that seems very mathematically sound, but it actually has implementation issues attached to it. The number of arguments or parameters. Well, I'll throw that under another bucket, just to kind of wean it into another direction. But that's a good suggestion as well. But remember, in the context we're talking about algorithms, we're talking about where we always are given a problem, and then we know what those parameters look like already. So these are things I don't really have much control over. So I'll throw it under actually another category that I think that might fit nicely under. difficulty to modify or augment. So for example, a lot of the problems that you've run into in previous classes, such as, for example, linear search over here, or some of the sorting algorithms, many of them are very easy to pick up and adapt to use in other problem settings. You've probably seen this with data structures, for example. If you're talking about, say, a stack data structure, you may, for example, have learned previously about linked lists, for example. When you see a linked list, it's rather a nice feature to have it so that you can model many things with linked lists. So that's just one example of what I mean. But this is another context for which I could say, okay, so if I have one problem, and here's an algorithm that solves that problem, what if I make a small tweak to the problem itself so that I could solve a different problem? That's maybe a nice appealing feature it might have. So such as changing the parameters or arguments it may have. Two others I want to point out are conceptual simplicity. So this is one that's related to what we talked about with implementation. That says conceptual. The A sort of melted into this blur here. It says conceptual simplicity. For example, if I was trying to teach you a bunch of algorithms, I would like it to be very natural to be able to communicate it to you. And of course, the final one is running time. The efficiency of the algorithm with respect to time. So what we're going to do next time is we're going to focus on a couple of these. We're going to focus on this one and this one. We're going to talk about complexity, okay, everybody? So when we come back on Tuesday, we'll talk about complexity analysis. So I'll say thank you very much and have yourself a beautiful day, everybody. I'll see you later.